Hey everybody, welcome back to Spatial Statistics. Just full disclosure, my stylus is malfunctioning today, so we will have to do the best we can. I really can't get out and buy one between the time this needs to be uploaded and now, so we will just have to do the best we can. It took me a little while to write what's on the screen, so here we go. We will get through it. It'll be frustrating for both of us, I am sure. We've been talking about the variogram. It's an important exploratory tool for geostatistical data. Geostatistical data is when you have a variable of interest that is measured at a set of fixed locations with known coordinates. So the first thing we do is we compute half the square differences for all pairs of observations. This gives us our variogram cloud values. We then identify reasonable distance bins in which we average these gamma values, and we produce from this the classic variogram. From the classic variogram, we can tell things like the nugget, the sill, and the range. If you don't know what I'm talking about when I say sill, nugget, and range, please do watch the previous video because I'll be referring to these concepts in this video. Or actually, we can go back and take a look. Here's an example. That's a good idea. So the nugget is the value that our variogram approaches as it approaches a distance of 0. So the value that our variogram approaches is around right here. So this is the nugget. The sill is sort of the maximum, call it stable value attained by the variogram. So that's right there is the sill. The sill is also an estimate of the total variance, sigma squared. The nugget is an estimate of the non-spatial variance. The difference between them is called the partial sill. And the partial sill is the estimate of a spatial variance, the amount of variability that is due to spatial correlation, spatial location, spatial process. The distance where our variogram reaches its sill the distance where our variogram reaches its sill is called the range. In this case, it will be measured in meters. And this is the distance at which data are correlated. Everything that is farther apart than the range is no longer correlated. Everything that is within the range, within the buffer, all data within, call it 4 kilometers, are spatially correlated. To different degrees, of course, to different degrees. Something that is 4,500 meters apart is going to be almost uncorrelated. Things that are 2,000 meters apart are going to be more correlated. And that's due to the shape of the variogram right here before it reaches the sill. Okay. We can reformulate and extend the variogram. And the first way we do this is by looking at the co-variogram, and it kind of is what it sounds like. Co-variograms track the similarity in the data as a function of distance. So how similar are the data when locations are similar? Similar locations means the distances are small. In a roughly speaking way, it's sort of the inverse of the variogram. So similarity in data is measured by the covariance. So the population covariance formula is right there, but now we need to map it to our spatial statistics world to understand a little bit, because we don't have X and Y. We have a variable measured at one location and that same variable measured at the other location. So what does that look like? Well, The spatial covariogram, or spatial covariance, is looking sort of like this. And I just keep struggling with my stylus, but I'll be trying my best to stay calm. All right, so I just mapped the variable measured at the ith location, the variable measured at the jth location. Notice that the mean is the same because it's just the overall mean of your observed data, regardless of location. And even further, remember that we assume by second order stationarity that our mean is equal to 0. This is the same thing as saying that we work with the residuals. We look at the residuals. And if you remember some facts about the residuals, the mean is equal to 0. So if the mean is equal to 0, then what you have is sort of just the expected cross product of observations. And by the way, expected cross product of observations, if you think about a checkerboard pattern, and in a checkerboard pattern, that is a classic example of negative spatial covariance because nearby observations have opposite signs. You think of the filled in area as being positive and the non-filled in area being negative. Then my neighbors, the observations that are near me in distance, have the opposite sign, right? And so this expectation is going to be negative. So this is an example of negative covariance because your neighbors are the opposite of you. We typically in spatial correlation think of positive covariance because your neighbors are more alike, right? So positive numbers are near other positive numbers and negative numbers are near other negative numbers, which of course then the expectation, the average, expectation is just the population word for average, will result in a positive covariance. So the code for fitting a covariogram is quite easy. You just set covariogram equals to true, and we can produce a cloud. So just like you can compute half the square difference between every single pair of observation, you can also take the cross product of every pair of observations. So for example, right here on the bottom, we have a negative covariance when the distance gets very large. Do I really think that is reflective of something very interesting happening in the process? No, this is my way too small sample, so stuff is going to be very noisy here. But compare this general trend with that of a variogram. You will notice that there's a general decreasing trend. That is, the covariance between pairs of observations tends to decrease as the distance between them increases. So the other thing to notice here, look at the cases where distance is 0. So for example, point number 2, point number 5, 9, and 14. What is happening there? That is where the distance is 0. When the distance is 0, you're actually taking the covariance of an observation with itself. If the distance is 0 or even near 0, then you know that really would have loved for my stylus to work today, and I'm going to stay calm. I'm just really going to stay calm because it seems like the harder I press, the worse the result. If the distance is equal to 0, then I'm actually looking at the covariance of an observation with itself. The covariance, in general, the covariance of a variable with itself is actually equal to the variance. And because my stylus is behaving this way, I will refrain from showing this to you in a mathematical statistics way. The covariance of an observation with itself is the variance. By the way, the correlation of an observation with itself is 1. Everything makes sense because the correlation is the covariance divided by the variance. So what we are doing when we are looking at the covariances at distance equal to 0, we're estimating the variance, or sigma squared, or in other words, the CIL, total variance. Yep, we're going to estimate the CIL, or total variance. Remember, this is the co-variogram cloud, so in order for us to get a better estimate of the CIL, we would just average all the 0 distances together. So why did these not exist inside of the variogram? Well, if we're looking at the case where the distance is equal to 0, and we know then that this is true, by the way, this is due to the fact that we're using a real distance. That's one of the axioms of a distance metric. If the distance is 0, you're looking at exactly the same location. So if we're looking at a half the square difference between the variable measured at the ith location and the same variable measured at the ith location, that is just equal to 0. So the variogram actually starts at 0, 0. And so R doesn't compute that because no matter how many bins you have, or what your variable y is, the origin of the variogram is always 0, 0. And R does not compute half the square differences at a distance of 0. It starts computing at the next distance bin. So that's why when I say what the nugget is, I always say that's the value as your variogram approaches 0 from the right, not exactly equal to 0. Because if you take in the variogram, at a distance of exactly 0, you're going to be down there at y of 0. So I mentioned that covariances are unbound and have weird cross-product units. We don't like that. That means I can't tell how large is large and how small is small. That's bad. So we prefer correlations. How do we turn a covariance into a correlation? We take a covariance and we divide it by the variance, and that gives us a correlation. So to go from a co-variogram to a correlogram, all kinds of fun words, we simply divide by the variance, or the CIL, right? Because in spatial statistics, the total variance is the CIL. So you take all of these values, and you divide them by the CIL, by sigma squared, and you're going to get a correlation, a cross correlation between observations. Okay? So on the left, we have a covariogram cloud, very difficult to interpret. Notice the spike at a distance of exactly 0, right? These are all covariances of the data with itself, right? They're estimating sigma squared. If I identify reasonable bins, distance bins and then average my covariances inside each bin, just like we do for the variogram, we're going to get what I have on the right, which is kind of the classic binned covariogram. Remember that I'm dealing with a z-score. And so the variance we know for a fact is equal to 1. Look at what's happening. At the distance of 0, my averaged covariance produces a 1. We like that. That makes sense, right? There is the value of the covariogram at distance equals 0 is the CIL, right? So CIL is our covariogram at a distance of 0. Stylus. Okay. The nugget is then this discontinuity as we go from a distance of exactly 0 to something just beyond 0. That's that non-spatial variance. So this right here is our nugget. This right here is our CIL. This distance is the nugget. And then the range is the distance where the covariogram goes to 0. Range. We know that's the distance where data become independent, spatially uncorrelated. So it's the range is the distance where the covariogram goes to 0, is near, call it 0. And I'm using teeny tiny bins here of about ½ a kilometer. So the range looks to be like it's longer here than in the variogram picture, right? In the variogram picture, my range was about 5 kilometers. And in this picture, it looks like it's, oh, I don't know, somewhere over here between 5 and 10 kilometers. But recall that, you know, we have noisy data. And if you think about the line, this is 0.2, right? So this is the covariance of 0.2 with a variance of 1. So this right here is actually correlation of 0.2. Right? These are covariances, but our variance is 1. Correlation is covariance divided by the variance. So because we're working with a z-score, these numbers on the y-axis are also the correlations. So if you think about the fact that this point right here is a correlation of 0.2, and you think about how much you care about a correlation of 0.2, that is not a ton. If I told you something was correlated, if I told you your effort in this class was correlated with your final grade at a rate of 0.2, you would never take this class. So that is to say, you know, the 0.05 line, if you will, is just out here, 0.05 line. And so there you can sort of see that the range actually agrees a little bit more. But it just might be that it's easier to see what the range is using a covariogram when the covariances go to 0 than the variogram, which is when the variogram attains its CIL. The only reason I'm able to pick it off here is because I know what the CIL should be, 1. Why 1? I'm working with a z-score. Okay? So, covariogram. Notice another thing. Remember I said that the covariogram is essentially a variogram, kind of inverted variogram. Look at the shape. Look at the shape. The covariogram looks like this. The variogram is its flipped version, right? It looks something like this. Remember that in a variogram, we don't observe a distance of 0. R doesn't compute that for us. So the nugget effect is as distance approaches 0, right? So the red line is the variogram, the co-variogram. The purple line is the variogram. Okay, co-variogram starts high, gets low as distance increases. The variogram starts low and gets high as distance increases. All right, the next step is the variogram map or the co-variogram map. At this point, I am sort of just referring to them interchangeably because, you know, in the code, it's just setting this co-variogram equals true, and conceptually, variograms track differences in data as a function of distance. Co-variograms track covariances in data as a function of distance. I actually think covariograms are more intuitive, far more intuitive, but variograms are more frequently used in the literature. I think for historic reasons. So the big idea in a covariogram map is we're going to divide our spatial domain, London, whatever we're doing, the state of Colorado, into square bins, and then systematically traverse the region in every possible direction, and then bin either variogram values or covariogram values in those directions. And I'll give you a picture in just a sec. All right, so we systematically go through and compute either the variogram or the covariogram in a variety of distances and a variety of directions. Here is this direction and distance. Here is this direction and distance. Here is the same direction, different distance. So we're just gonna traverse our map in a variety of directions and with a variety of different length vectors and compute either the variogram or the covariogram value each time. So this now, you're expressly considering direction. This is the first time in this class that we are expressly considering what is the direction of the covariance, what is the direction of our variogram. And this can reveal directional spatial dependence. So in the discussion board, somebody asked, well, what is a common reason or what is a common process that has a direction? It's anything that where there is some kind of transport vector. So think of air pollution being transported by wind. Think of water pollution being transported by a current. Think of nutrients or abundance of plankton being transported by a current. If some species of fish prefers cold water over warm water, you might have a direction of the abundance because of the current, water current. If you're dealing with geology, there could be things like faults and folding that happens inside the earth that can induce directionality. It's anything to where directional spatial dependence is any time where spatial correlation is bigger in one direction than another direction. So they are definitely less noisy than variogram clouds, but you will see that it could still be hard to, in a realistic scenario, and London Asthma, I keep using it as a sort of a realistic scenario. It's 1,000 data points. It's a fairly realistic scenario. It's very difficult to tell what the nugget, range, and sill are. So if what you're trying to get is some kind of like a summary measure per region, don't start with a covariogram or variogram map. And the shape of the region can make weird shapes inside of your covariogram / variogram map. Let's see what one of these guys looks like. So just as before, if you take a look at the code, not much changes because we still simply estimate it by saying covariogram is true. So I'm going to look at covariances, not variogram values. And now I say map equals true. So what it produces is kind of a square like this. On the y-axis, I have how far we moved in the vertical direction. On the x-axis, I have how far we moved in the horizontal direction. And so we have every possible direction, right? In the middle, I have a change of distance in the x direction of 0 and the change of distance in the y direction of 0. So the middle square is estimating that covariance of our observation with itself, or that means the sill or the variance, because the distance is equal to 0 or approximately 0. These have bins, right? So that blue square right there is basically averaged covariances of data within a 1 kilometer bin in any direction. Does our estimate get better or worse as the bins get smaller? As the bins get smaller, we get closer and closer of getting this right. So as bins get smaller, we get closer and closer of taking the covariance of an observation with itself, which of course, again, is estimating the sill or the total variance. Do these maps tell us anything interesting? So maybe this is the key question. Do these maps tell us anything interesting? You look at covariogram / variogram maps to try and gather a sense of direction. So let's take a look. Each one of these legends is slightly different because the bin size and the number of bins is slightly different. Let's look at this bottom right at first. So the blue colors, roughly speaking, the blue colors indicate a positive covariance, and the pink and red colors indicate either no covariance or negative covariance. So look, as we go farther apart, in this north-south direction, data are correlated to 1, 2, 3 boxes. Each box is 3 kilometers apart. So in the north-south direction, my data are correlated at a clip of about 9 kilometers. Look at what happens as we go in a different direction. For example, this direction, which is the northwest-southeast direction. We have to go a lot shorter distance for that covariance to go to 0. So it looks like, from this map, the correlation in the north-south, when we're changing y's, but not changing x's, is a bit stronger than the correlation along this direction, the southeast northwest direction, when we're sort of diagonally changing y's and x's. Is it strong? No. And in fact, you know, when you're looking at the magnitude of these covariances, once you go 1 bin out, so that's 3 kilometers. By the way, 3 kilometers is also very, very close to what I believe the actual range is. As we go 1 box out in almost every direction, we basically go to a covariance of 0. So this is actually an example of a fairly omnidirectional covariance that maybe has a hint of stronger covariance north-south than other directions. So let's look at it a little bit more. To be clear, this box number 1 says that we're going to traverse the map. The map on the right gives us a map of the z-scores, by the way. That's why I have negative and positive values. So box number 1 says we're going to traverse the map in the north-south direction by 3-kilometer vectors and then average covariances into these 3-kilometer bins. So look at my scale here on the bottom. 3-kilometer distances, roughly like this, and north-south direction. All right? So I start from every point and I go north, directly north and south by 3 kilometers. And I do this all over the map. I traverse the map. And now I take the average covariance of all of those points and I map it, all points that are 3 kilometers apart, north-south, right? Because these are not directional. These are not directional. These are actually just, rather they're not pointed. These are directional, they're not pointed. As in, the north-south vector goes like this. That is not the vector north. So that is why my covariogram map is mirrored along this horizontal line right here. So I traverse my map everywhere, by 3-kilometer north-south distances. I take all of those points and I average my covariances and I put them right there. That's a positive covariance. So points are positively correlated to points that are 3 kilometers straight north of that. Why 3 kilometers? Because here I have 15-kilometer cutoff with 5 bins, right? 1, 2, 3, oops. 1, 2, 3, 4, 5 bins. This stylus is going to be the end of me today. Okay, let's do another one. Number 2 is doing the same thing, just using point number 2 is doing the same thing, just not 3-kilometer vectors, but 9-kilometer vectors. So now 9-kilometer vectors are about this long. So I'm going to traverse my map using 9-kilometer vectors. And of course it does this programmatically. And we're going to average the covariances. I'm going to average all these covariances into this bin. And of course we're going to fill up the map, right? And you can see that what this returns is something that is actually pretty close to 0. So 9 kilometers directly north-south, all data that is within 9 kilometers of other data, where we go directly north-south, is actually pretty uncorrelated. And now, of course, number 3. We keep going in every direction, in every possible distance vector. All right, so now we look at number 3. Number 3, we traverse the map in the east-west direction using 3-kilometer vectors, okay? I know how big my 3-kilometer vectors are. My 3-kilometer vectors are about that big. So again, take the map and traverse in using 3-kilometer vectors, average the covariances of data that is within 3 kilometers east-west directly, right? East-west directly, take that average of covariance Why covariance? Because it's a covariogram map, and put it right there. All right, 9 kilometers, 369 would be here. If I did the same thing, just using 9-kilometer vectors, take the average covariance, put it right there. Again, what this is supposed to do is reveal any possible directional covariance in the data. What the picture on the left does not reveal that there is much. So another way to think about it is you're looking for elliptical shapes. You're looking for elliptical shapes. And you sort of see one here. You sort of see one here. But again, keep in mind the scale. Admittedly, if you thought that variograms were frustrating, then variogram maps are exponentially so. It really can be like reading tea leaves, especially if we go back here. You know, what are you really supposed to tell from these kinds of pictures? You know, is there, looking at this top left panel, is there anything going on there? I don't know. I don't know. Maybe I'm seeing something elliptical. Maybe I'm not. Maybe I'm seeing like something that looks like that there. Maybe I'm not. You really, I'm not saying that I'm particularly good at reading these variogram maps, but that is really what these exploratory tools produce. They really can be like reading tea leaves. Now, what can we do about it? What if we bin distances like we did for the omnidirectional variograms, the directionless variograms, but just along a few directions of interest? What if we don't care about every possible little direction? What if we care about just maybe this direction versus this direction versus this direction versus this direction? By the way, that's 4, right? 1, 2, 3, 4, and I've just covered the 4 cardinal directions. If you're getting frustrated with the exploratory tools, I hear you. We're moving on to inferential statistics next week. But this stuff still has its use as long as we understand its limitations. So we're basically going to pool our covariogram maps in specific directions. Just like you were pooling your cloud into distance bins, here you're going to pool your covariogram maps into specific directions. So the typical approach is the one I just drew, right? 0 degrees, 45 degrees, 90 degrees, 135. Depending on where you start counting, 0, 90, 45, 135, the 4 cardinal directions. What does this look like? So again, I'm looking at covariograms. You could, if you wanted to, be looking at variograms. The way you look at these directions is by specifying this alpha bit in your code. And again, this is a covariogram. So you're looking at covariances. So this is annoying. In the GStat package, 0 degrees is north. I repeat, in the GStat package, and only in the GStat package, 0 degrees is north. In a different package, 0 degrees might be the east-west line. But in the GStat package, 0 degrees is the north-south line. So as we pool our variogram map along the north-south line, we get a covariogram that looks like this. Okay, here is the sill. Right around, oh, I don't know, here is the range. Right around there is the nugget. Okay, rotation. Rotation is clockwise. the rotation in G-stat is clockwise. 0 degrees is north, the rotation is clockwise. That means 45 degrees, we start here and we rotate by 45 degrees. So this is, of course, our northeast southwest line. Here is the sill. Here is the nugget. Notice it's a little bit smaller than the nugget in the north-south direction. And so is the range. The range, too, is a little bit lower than in the north-south direction. Remember, we should expect this, right? In the north-south direction, the range looks to be somewhere like 9 kilometers. In the east-west direction, the range looks like something like 3 kilometers. 90 degrees, remember 0 degrees is north, rotation is clockwise. So we started here and we rotated it by 90 degrees. So 90 degrees is now the east-west line. Again, sill, nugget, range. Pretty similar, honestly, to the northeast-southwest line. And finally, the 135, we rotate a little bit more. That's now the southeast-northwest line, sill, nugget, range. The range is probably a little bit higher than it was in the northeast-southwest direction. By the way, this is as good a time as any to define the concept called anisotropy. And anisotropy is the lack of isotropy. Isotropy is when spatial correlation does not depend on direction. We have mild evidence at best, that the covariances differ with direction. There are some minute differences. And again, that too, we could have probably extracted from this covariogram map, that the north-south direction is somehow different. All right, so now we practice, right? North is 0, rotation is clockwise. North is 0 degrees, rotation is clockwise. That means that 30 degrees, right? 30 degrees is basically the northeast-southwest line. 75 degrees, right? Here's 90, so we don't quite get to 90. Is still roughly the northeast-southwest line. But it's further rotated. It's closer to 90 degrees. You know, maybe it's something like this. 120 degrees, you rotate past 90. And 165, you rotate further than that, right? North is 0, and you rotate clockwise. All of this said, I think that there is mild evidence of anisotropy with London asthma data. I think that the north-south line, whether I look at this covariogram map, and of course it's, you know, it's symmetric around dy equals 0. So the north-south line is different than all other directions. And that is best picked up by this directional covariogram. That was a lot of hand waving and a lot of faulty stylus. I'm apologizing for the faulty stylus and apologizing for the hand waving. We are now wrapped up with this particular set of exploratory tools. They're important. If you know, we will see what a definitive anisotropic case looks like. Hint, it's the scallops. And so look out for our second in-person activity for this Thursday. Thank you guys very, very much. I'll also be posting the homework later this week. So stay tuned for that. Thanks so much. I'll see you guys on Thursday.